Hello, students. Welcome back for another lesson on phases of matter. And so, yesterday, if you recall, we left off talking about the three main phases of matter. And what were the three first phases of matter we discussed? Good. And what was the fourth phase of matter? Excellent. And we also discussed those other phases that are being kind of thought about at this point in human history. But today we're going to continue with our discussion of phases of matter by talking about phase changes. The changes that take place between the various phases of matter. So let's get right into it. Make sure your books are open, and let's pick up here on phase changes. And in general, the change from one phase of matter to another, regardless of which phase we might be talking about, is due to the changes in heat energy. We spent a whole week on heat energy, so you know a little bit about heat energy now. But these changes that take place between the different phases, and right now we're going to focus on solid, liquid, and gases. But those changes that take place between solids, liquids, and gases are a direct result of changes in heat energy. So I want you to keep that in mind as we go through our lesson today on the changes that take place between phases due to changes in heat energy. And again, think about what heat energy is, the kinetic motion of particles of matter. So with that in mind, let's get started right away with our first change in phases. And we'll introduce this one with a little video clip.
You cursed brat! Look what you've done! I'm melting! Melting! Oh, what a world! What a world! Who would have thought a good little girl like you could destroy my beautiful wickedness? Ah, look out! Look out! I'm going!
Does that scene look familiar to you? It probably does if you ever watched the infamous movie Wizard of Oz and the Wicked Witch was melted. Her body was turned from a solid to a liquid simply by Dorothy pouring a bucket of water on her. Because as the story goes, you pour water on a witch and she melts. I don't know if that's true or not, but that's what happened in the movie The Wizard of Oz. So, melting, the change that takes place from going from a solid to a liquid, we call it melting, from a solid to a liquid. That probably doesn't surprise you. That's probably a term that's rather familiar to you, especially this time of year as we get closer to winter time. You may be thinking of building snow forts or snowmen when the snow arrives, and eventually that solid snow will melt. And we know that it melts when it gets warmer. In fact, speaking of heat energy, melting is due to an absorption of heat energy. Now, as we go through this lesson, I'm going to pause at points and I want you to really think about what is happening from a scientific point of view in terms of heat energy, because believe it or not, you may become a little confused with certain things. So here's the deal. Melting is due to an absorption of heat energy. Think of the word absorption. Maybe think of a context for that word, absorption. What does it mean to absorb something? Maybe you think of a sponge or a paper towel absorbing moisture or water from a tabletop. And if you think of a sponge or a paper towel absorbing water, what happens to the surrounding area? Does it get drier or does it get wetter? It gets drier. Think of it again. We take a sponge and absorb the water from a countertop. What happens to the countertop? It dries out. You are drying it. Now think of this in terms of heat energy. Melting absorbs heat energy. So if melting is absorbing heat energy, what do you think happens to the surrounding area? Does it get warmer or does it get cooler? Again, think about it, and hopefully your answer is it gets cooler. If something, a substance, is, again, melting and it's absorbing heat energy from the surrounding area, then the surrounding area gets cooler because heat is being absorbed into that substance. Now, hopefully you can catch on to that logic because I'm about to confuse you even more. So if you need to pause this and watch it again, go back to the sponge part. Think about the water being absorbed, drying the surrounding area, and then think of the heat energy being absorbed, getting cooler in the surrounding area. So let's build upon this when we now talk about the opposite function, which is freezing. When you freeze something, it goes from a liquid to a solid. It is the reverse or the opposite of melting. Now, that probably makes total sense to you so far, but let's continue with this idea of freezing. Let me show you a little video clip of ice crystals growing. Isn't this cool? I mean, check it out. Look at this. We're actually watching the freezing process. Water vapor in the air is going from, well, actually from a liquid as it condenses and then it freezes. I mean, isn't that just awesome to watch something freeze? I think that's really cool. Now, obviously, this is time lapsed and it is under magnification, but look at that crystal structure. It's like the formation of snowflakes right from scratch. Now, as we have that beautiful image in our minds, let me explain what's happening from a heat energy point of view. Check this out. Freezing, again, going from a liquid to a solid, and most of us think in terms of water, is due to a release of heat energy. Think about it for a moment. When water goes from a liquid to a solid, it's because that liquid has to release heat energy to cool off, to go from a solid to a liquid. But when that is taking place, what happens to the surrounding area? Does it warm up or cool off? Did I make you think about that a little bit more? Let me ask the question to you again. When something freezes, does the surrounding area get warmer or colder? It actually gets warmer. That might not seem to make sense to you at first, but again, if you need to replay this and think about it a little bit more, feel free. But let me ask you another question. Now, I'm old enough, I've been around for enough winters to experience certain things, and I have noticed something because I am the one in my family who does all of the snow shoveling, and I like to keep up with the snow shoveling so that it doesn't become overwhelming at the end of a snowstorm. And I've noticed something over the years. I've noticed that before a snowstorm arrives, it can feel really, really cold out. Oh, it's just a bitter cold that goes through my bones. But I've noticed that when it starts snowing, in other words, when the snow starts falling out of the sky, in other words, when that liquid moisture in the air begins to freeze, it actually feels a little bit warmer to me. Now, not a lot. I'm not talking about like shorts weather and going to the beach, but my body senses when it begins to snow by it feeling a little bit warmer. Have any of you ever experienced that at all? Now, why is this? Well, I'm going to give a little bit more info here and then give you another scenario that might boggle your mind. So, it's called the heat of fusion. And while you're writing this down, I want you to reflect on the topic we covered on heat energy. And I want you to think about heat energy and the word calorie. Do any of you remember what a calorie is? What is a calorie? If you said a unit of heat, you're absolutely correct. Now, that unit of heat that we call a calorie, how do you quantify that? How much heat is a calorie? You can pause for a moment and look back in your notes. See if you can find the answer to that question. How much heat is a calorie? Well, if you found that a calorie is the amount of heat required to increase the temperature of 1 gram of water 1 degree Celsius, then you're absolutely correct. And I asked you a series of questions during that topic. Well, if it takes 1 calorie of heat energy to raise the temperature of 1 gram of water 1 degree Celsius, how many calories are required to increase the temperature of 1 gram of water 10 degrees Celsius? And you said 10. And then I asked, well, how many calories are required to increase the temperature of 1 gram of water 20 degrees Celsius? 20 calories. Do you remember that sequence? Well, think of ice cold water at 0 degrees Celsius. How many calories would be required to increase the temperature of 1 gram of that 0 degree water up to 100 degree water at the boiling point of water? Hopefully you said 100 calories. That's a lot of heat energy. Now, you would not want to bathe in 100 degree water, or you'd cook yourself, literally. You'd be boiling your flesh. But think about the heat energy required to go from 0 degrees to 80 degrees water. It would require 80 calories per gram. Now, 80 degree water is still hot enough to cook you at a slow simmer. 80 degrees Celsius is super duper hot. You would not want to take a bath in 80-degree water. Remember, body temperature in the metric system is 37 degrees Celsius. So a bath at 40 degrees Celsius would be a warm bath. 80 degrees Celsius, again, it's warm enough to simmer your body into a slow cook. But look at this. The amount of heat energy required simply to change from a solid to a liquid, and here we're talking about water, is 80 calories per gram. In other words, a 1 cubic centimeter, 1 milliliter, 1 gram of water that is liquid or solid requires 80 calories of heat energy to change from a liquid to a solid or the other way around. This amount of heat energy is called the heat of fusion. Let me explain it more. Let's say you've got a gram of ice and you measure its temperature. What is the temperature of 1 gram of ice? Ice, baby. It's 0 degrees. Now, let's say we have 1 gram of ice water. What is its temperature? 0 degrees. To go from 0 degrees ice to 0 degrees water, the temperature doesn't change at all, and yet we still have to add 80 calories of heat energy per gram. To say it another way, it takes an enormous amount of heat energy just to go from a solid to a liquid with water. And conversely, the opposite is true. To go from a liquid to a solid requires also 80 calories of heat energy. That's a lot of heat energy just to change from one phase to another without the temperature changing at all. Stay tuned for our lab activity to see how we can illustrate that. But now I have a question for you. Let's pretend that you are an orange farmer. You grow orange trees, and your livelihood depends upon your orange crop. And let's say you live in Florida, which is where a lot of orange farmers live. Now, let's say you're watching the weather report, and this does happen on occasion. And boy, it's before harvest season, and there's a cold snap moving through northern Florida. In fact, the temperatures tonight are going to go below the freezing point. You say to yourself and your family, the temperatures are going to get awfully cold tonight, but it's too soon to harvest all of your oranges, and you've got thousands of acres. There's no way you can do it in one night anyway. And you realize, and if you don't believe me, by the way, take an orange and put it in the freezer. What happens to an orange when it freezes? Do any of you know? You might say it freezes, and that's true. And there's a lot of water in an orange. And so when an orange freezes, it cracks open because the water expands. And so it bursts the orange, dripping orange juice all over the place, which then freezes on the outside of the orange, and it makes a sticky, icky mess. Now imagine you're an orange farmer. Are you going to be able to sell any of those oranges that have exploded and made a icky, sticky mess because they freeze? The answer is probably no. There's no way you're going to sell frozen oranges. So you scratch your head and realize it's going to get cold enough to freeze all of my oranges. If my crop freezes, I'm done. I have no money. What are you going to do? pause the video to think about what are you going to do with your hundreds of acres of oranges and you've only got a few hours to spare. Well, I'll tell you what orange farmers do. They ride trucks up and down their orange trees and spray them all with water, knowing that it's going to get cold, cold enough to freeze that water. What? What? You might say to yourself, why in the world would an orange farmer spray water on his orange crop knowing that the water is going to freeze? Isn't that going to freeze all of his oranges quicker? Well, were you paying attention a moment ago? Because I can tell you this, the orange farmer paid attention in 8th grade science and learned about this thing called heat of fusion. You see, when water freezes, when it goes from the liquid to the solid phase, remember what we said before about freezing? Freezing releases heat energy. The surrounding area gets warmer. And when we're talking about water, that heat energy is 80 calories of heat energy per gram. So if you're an orange farmer and you spray your crop with water, and that water freezes, it actually creates an insulated thermal energy cocoon around the oranges and makes the oranges warmer and prevents them from freezing. Isn't that cool? In fact, it's kind of the same principle that is used by the Inuit people, otherwise known as the Eskimos of the North, where they build igloos and build a fire inside, and they snuggle in next to the fire to stay warm, and it kind of melts the ice structure within the igloo, and when the fire goes out, that water freezes. Why don't the Eskimos inside freeze? It's because of heat of fusion. Even though the temperature might not change, there is a significant amount of heat energy that is released when water freezes. So think about that as we continue with the next phase change. And the next phase change is from a liquid to a gas. And as we talk about going from a liquid to a gas, you might automatically think, oh, that's evaporation. Well, it's not exactly the same thing as the phase change that we're going to be mentioning here. It's technically called vaporization. Vaporization is the phase change going from a liquid to a gas. Evaporation is basically vaporization just on the surface. So vaporization, again, going from a liquid to a gas, is it requires a change in heat energy. Now, let's focus on this, just like we did with the solid liquid change. Vaporization is due to an absorption of heat energy. So when something vaporizes, I'm going to ask you the same question. When something vaporizes or goes from a liquid to a gas, does the surrounding area get hotter or cooler? It actually gets cooler. When a liquid vaporizes, the surrounding area gets cooler. Why? Because that liquid, in our case water, has to absorb more heat energy in order for the molecules to start moving around fast enough to go from the liquid, boom, to the gas. So it requires an absorption of heat energy, which causes the surrounding area to get cooler. So let's take that in reverse. The reverse of that is called Condensation. Condensation, you see this all the time, this time of year when it's cold outside, but it's warmer inside, especially in a school bus or a car. You can get condensation building up on the gas. And condensation is due to a release of heat energy. So when something condenses, when something goes from the gaseous phase of matter to the liquid phase of matter, what happens to the surrounding area? Does it get hotter or colder? It gets hotter. Now, let me ask you this. How many of you have ever been outside in the wintertime and your hands get cold and you do this in your hands? You breathe in your hands, right? It warms them up pretty quickly. Why? It's because of this. You are breathing out water vapor, which is the gaseous form of water. That water almost instantly condenses onto your hand, goes to the liquid form. Gas to liquid, gas to liquid. What happens to the surrounding area during condensation? There is a release of heat energy. And so, yeah, it's pretty effective to breathe water vapor into your hands to warm them up. But here's the deal. It's only temporary, because if it's really, really cold outside, that liquid water won't stay liquid too long and will eventually freeze around you. And if the process continues, if you've ever read Jack London's little story called To Build the Fire, well, you know what the end of that story is all about. So the best thing to do is to get out of the cold, go inside and have some hot cocoa. That will keep you warm on the inside and the out. But condensation is due to a release of heat energy. But get a load of this. If you thought 80 calories per gram, that heat of fusion was a lot, going from solid to liquid, get a load of the heat of vaporization. The energy required to change from a liquid to a gas is 540 calories per gram. Let that sink in for a moment. 540 calories per gram. It takes 100 calories to go from ice cold water to boiling water. This is more than 5 times that amount of energy. That's a lot of energy. So what do you think is worse? Getting burned by boiling water or getting burned by steam? If you said boiling water, you're absolutely wrong. And some of you might be thinking, well, wait a minute, I've boiled pots in the kitchen before and put my hand through the steam, and that wasn't nearly as bad as putting my hand in a boiling pot. And you know what? You're right. But you have to compare apples to apples or oranges to oranges. The point is this: it is per gram. So if you have a gram of boiling water and a gram of steam, the steam has 540 calories more heat energy in it than the boiling water. Think of a teapot, one of those whistling teapots with the steam being forced out, a little stream. Don't put your hand over that because the steam is more concentrated. Or maybe if your homes are older and you heat your home with forced steam, if one of those pipes burst and you have forced steam coming through a pipe, you don't want to go anywhere near that, because that concentrated steam with more mass will inflict a much greater injury. In fact, steam gram per gram, could literally melt the flesh off of your body. It has so much heat energy. That would be bad. Okay. So the heat of vaporization, 540 calories per gram. And that's when we're talking about water. Now, there's one more phase change I want to mention, and this is not a common one here, although it is a common one on Mars. And it's going from the solid to the gaseous phase. You may be familiar with this if you've ever used an ice cube tray in your own freezer. And you fill up an ice cube tray with water, you put it in the freezer, and you turn it into ice cubes because the water freezes. But let's say you forget about it for a long time. Like maybe you don't use ice cubes in the wintertime. So you made ice cubes in July and you don't use them until next June. So they've been sitting in your freezer for almost a year. Do any of you know what happens to those ice cubes? They get smaller. If you don't believe me, try it. They get smaller. Why? Not because they're melting. Hopefully they're not melting or you've got a problem with your freezer, but they're undergoing something called sublimation. And let me show you sublimation here. Sublimation is more common in the context of dry ice. This is ice sublimating. This isn't water ice. This is carbon dioxide ice. So as it is changing phase because it's warming up, we call carbon dioxide dry ice when it's in the solid form because it's not melting. This isn't melting. There's no pool of liquid when dry ice changes, but rather just vapors are released. They call dry ice because it doesn't melt. It undergoes sublimation. It goes directly from a solid to a gaseous phase. That's what happens to water, by the way, on Mars. Because the atmospheric pressure, water doesn't melt on Mars. It sublimates right into the atmosphere, which is one reason why there's no liquid water on the surface of Mars today. So say bye-bye to the dry ice. And we'll move on now to our notes here and sublimation. Again, sublimation is when you go from a solid to a gas, and it is due to absorbing heat energy. Absorbing heat energy. So if sublimation involves absorbing heat energy, what happens to the surrounding area? It's going to get colder, which is why dry ice is oftentimes used in packaging of fresh foods and meat, because it doesn't melt, it sublimates. And when it sublimates, it's making the surrounding area colder, keeping your food fresh and cold. So those are the various phase changes that we are going to be discussing. And I'm going to say we're out of time for today. So we're going to save the gas laws for tomorrow. So for now, I'm going to say bye-bye.